talk sort of the meat and potatoes of quantum mechanics. We've got sort of the baseline idea that you can treat particles as waves and waves as particles, and particle wave packets are these little blobs of waves that are particle-like and wave-like. We also know that there's a fair amount of statistics involved and probabilistic ways of looking at these particles and waves. And then we've talked a little bit about the implications of having this wave-particle duality on being able to determine uncertainty, knowing position versus knowing momentum or velocity, and how the wavelength of these packets relates to momentum and energy. So let's get into sort of the math of this. And so this brings us to a guy named Schrodinger, Erwin Schrodinger. He's German, and he sort of had this idea that because we don't have these definitive positions, these are no longer point particles, there's this uncertainty that we're dealing with. So if we want to know where something is, like if we want to make predictions, if we want to use the equations like we did in kinematics to decide where things might end up later and figure out later in time, if you know the initial conditions, what's going to happen, we need to know more about the wave function. And so if you know how to determine a particle's wave function, Schrodinger figured you could predict outcomes of experiments the same way we do in classical physics. So, we know the wave function gives us sort of the probability that a particle will be in a particular place, but we don't necessarily always know how to determine the precise location. So this brings us back to sort of this differential equation-y stuff that we did all the way back when we talked about waves at the beginning of the semester. So remember, wave functions, usually these sinusoidal things, are a solution to this differential equation called the wave equation. And just as a side note, particle waves and mechanical waves, this is not quite, we're not going to quite be doing the same thing as wave on a string or sound waves, because the wave function for particles is not a mechanical wave. It doesn't need a material medium to propagate. It describes the particle, but it's not part of the material. So we're just using this same concept to make predictions and try to do physics on these objects that behave differently than, say, like a classical particle. So anyway, this is the solution to the wave function equation. So if we go back, this is the differential equation, and this is the solution to that equation. This is, something we talked about earlier in the semester, but here's the wave number. We have wavelength, we have angular frequency, we have all of these things. But when we're talking about Schrodinger's equation, it's similar to the wave function, right? It's similar to that differential equation, and so it has a similar solution. The main difference here, though, is you're going to see this imaginary number show up, and I'll show you in a second why we have that. So the solution to this, the solution to that linear wave equation was a sine-cosine combination. Because of the imaginary numbers here, now we get sort of a similar solution, but it has this I here and here. And the reason we do this, it's sort of a way of indexing things. Here's the real version of the wave function, right? Here's the imaginary version of the wave function, and you can see this general solution includes both of them. And so you can always break the wave functions down into real and imaginary, and we'll see why that's useful in a minute. So this is the one-dimensional wave function of a free particle. To make it a little bit simpler, let's use something called Euler's formula or Euler's equation, and that makes it much less ugly with a bunch of sines and cosines. So remember, this is Euler's formula. It's e to the I theta is equal to cosine theta plus I sine theta. You can see there's a definite match here. So now you can rewrite your wave function in a very nice way that's much more concise. Okay? And the other useful thing about doing this way is we're going to talk a little bit about how the probability density, right, is always the wave function squared, but when you have imaginary numbers, squaring things gets a little bit trickier, okay? So remember, in order to square an imaginary function, you need to use something called the complex conjugate, all right? And a complex conjugate sounds really exciting and difficult, but it's really stupidly easy. So if you have something with imaginary numbers, to get its complex conjugate, anytime you see I, you just change it to negative I. So if you have A plus IB, now it's A plus negative IB or A minus IB. Okay? And the reason we do this is because when we square things, and especially when we square things with this, we're squaring things and we have the absolute value sign on the outside, we want to get a real answer. And in order to get a real answer, you have to multiply something by its complex conjugate, and that always gives you the real answer. Okay? Now, you can also, e to the ik, if it's negative, becomes positive e to the ik. So look, here's your value, here's its complex conjugate, right? So here's your original function, here's its complex conjugate. Original function, complex conjugate. Original, complex conjugate. Okay, so all we're doing is we're finding the complex conjugate, and what this tells us is when we square our wave function, we usually end up with the amplitude squared. So here's our wave function squared, right? You take the complex conjugate, you get the amplitude squared. All right. So going back to our wave packets, here's our wave function. Here's the real part of it. Here's the imaginary part of it. And here's the wave function squared. So here's the probability of finding something in that space, okay? And remember, this integral here represents the superposition of many different wave functions that we need to make these packets, right? This is a wave packet, this is a wave packet too. And we're going to get more into the details of this, but just follow along for now. So this brings us to stationary states. Now when we were talking about stationary states in terms of like the hydrogen atom, those were just different potential energy levels, right? So a stationary state in terms of the Schrodinger wave function solution, all right, here's our wave function. So this is our definite state of energy, wave function, time independent wave function, and then here's our time factor that depends on the energy, okay? So we're just restructuring this thing to go up there. Now, this only works for a potential energy that is 0. We'll talk about that in a minute. We'll have to bring that into the equation shortly. Okay? If you have, so this can't be used for non-zero potential energy, but these are good building blocks. If you have potential energy that's not 0, we can use this to solve some of the simpler problems that have definite energy. So here's our total mechanical energy of the particle, and here's the potential energy of the particle as a function of position. So it's possible, like with the hydrogen atom, to not have a totally defined energy. Okay, the wave function for a state can be written as a combination of definite energy wave functions, and that's the same way a free particle wave packet can be written as a bunch of sinusoidal waves that are superimposed on each other. So we have these functions of definite energy, and we can use them to form combinations to get other things. All right. So just with this in mind, let's go. Oh, here's a fun joke. Okay. Yeah. Just for your enjoyment. But let's talk a little bit about energy. Oh, and this is just some, sorry. These are just some extra notes. So let's talk about energy. And just in the classical way, right, we have these energy diagrams. And this is going to become important again now. So here's our potential energy, right? We know total energy is always constant. That's represented as this flat line. We have this is our maximum speed because wherever our potential energy is minimum, our kinetic energy is maximum. If we have our potential energy crossing our total energy, then these are our turning points, and anything outside of here is not an accessible energy state because you don't have enough total energy to reach that potential energy. Okay, so this is what we call the classically forbidden region. So the Schrodinger equation treats this, remember we know there's a relationship between frequency and wavelength and energy. So for instance, if we have our potential energy here, our total energy here, versus a changing potential energy and a total energy, we can see as potential energy changes, then kinetic energy changes, which means momentum changes, right, because the speed's changing, which means their wavelength changes, which means you change your wave function. So for this energy, because we have a constant energy, we end up with this constant wave function, right? You can see the frequency and wavelength don't change, right? The wavelength, de Broglie wavelength doesn't change. Over here, you can see where you have more kinetic energy, you have a higher frequency, right? Higher energy, higher frequency. So you can see over here, because we have more kinetic energy here, we get this more scrunched up wave here. Over here, where we have more potential energy, the wave's more spread out. Okay, so kinetic energy the higher kinetic energy leads to higher frequency. So let's try this out. Here are 3 de Broglie waves shown for particles of equal mass. We want to rank the slowest to fastest speeds of particles A, B, and C. Okay. So we know the de Broglie wavelength is going to be h over p, which is h over mass times velocity. They all have the same mass, but what we're going to notice is the faster things are, the shorter the wavelength is going to be. These things are inversely proportional. And you can see the wavelength of this and this look the same, but this one is bigger. So that means our speed for C is most likely the slowest, and A and B, since they have about the same wavelength, should be the same. Remember, the amplitude doesn't relate to the energy, to the speed, to the wavelength. It's just the frequency and wavelength. Okay, the amplitude's not relevant here. So even though B has a bigger amplitude, that's not going to impact the speed. Okay. Here's another question. Please take a minute and try this out, and then we'll talk about it. So basically, this is the kinetic energy. Remember, kinetic energy is 1/2 mv squared. So it should go the same way as speed since we know the masses are all the same. So that's going to be B again, because we know if C is the slowest and A and B have the same speed, then C should have the least kinetic energy and A and B should have the same kinetic energy. Now we're going to talk about potential energy. So let's try this one out. So the potential energies of particles A, B, and C should be just the opposite of the kinetic energy. So if you have a large kinetic energy, you should have a smaller potential energy. So that means A and B are still the same, but C should now be bigger. Okay. So now that we have a good idea of how energy relates to speed and all of this stuff, let's think about which potential energy function would be most likely to be associated with the wave function below. And remember, this is a potential energy graph. So wherever potential energy is big, okay, we are going to assume that kinetic energy is small. So that means that kinetic energy should be big. So this, if we're looking at this wave function, this should have large kinetic, and then this has large potential, and this has large kinetic. So we're looking for if we're looking at the potential energy, we're looking for something that's high here and low here. So high, low, low. This goes low to high, so this is wrong. This goes high to low, this is wrong. This goes high, low, high, wrong. So that means that only leaves this one, which goes low, high, low. So for solving the Schrodinger equation, we can calculate the wave function mathematically, or you can solve it conceptually like we just did based on the shape of the potential energy. So basically this is a second order differential equation which has a general solution that looks something like this. Okay, so the way that we go about doing this is there's only certain solutions for certain values of energy, and not all of the energy values are going to necessarily have solutions, because remember, only certain values of energy are allowed because the energy levels are quantized, because remember, energy is still quantized. So our solving strategy is going to be based on the shape of the potential energy. We're going to guess at solutions for the wave function. We will apply boundary conditions. If you've taken differential equations, this should sound pretty familiar, but I'll show, if you haven't, we will walk through it. And then we're going to normalize, like we did in the previous chapter, we're going to normalize the wave function by integrating over infinity and setting that equal to 1. So we know that all probabilities add up to 1. And then we're going to calculate allowed energy levels based on our solutions for the wave function. Okay, so that's the Schrodinger equation, and we'll work on, in the next section, applying it to some stuff that we're already familiar with.